And welcome back. As we continue our cosmic journey around Earth, let's go ahead and now shift our focus to that of keeping time. So let's start off with our conversation around the length of the day. The measurement of time is based around the rotation of the Earth. Throughout most of human history, time has been reckoned by the position of the sun and the stars in the sky. Now, only recently have we actually shifted to mechanical and electronic clocks to take over this function in regulating our lives. The most fundamental astronomical unit of time, of course, is the day, which is simply just measured in terms of the rotation of the Earth. There is, however, more than one way to define the day. Now, usually, when we think of a day, we think it as the rotation period of Earth with respect to the sun, which we refer to as a solar day. But this is not the only way to refer to a day. Astronomers also will use what's called a sidereal day, which is defined as the terms of the rotation period of the Earth with respect to the stars. So, we're looking at the celestial equator, we're looking at the position of the stars, and we're using that sidereal day to really kind of get that measurement rather than relying on the sun coming up and going back down. So what is exactly the difference between a sidereal day and a solar day? Well, a solar day is actually slightly longer than a sidereal day because Earth not only turns, but also moves along its path around the sun in one day. So to illustrate this, we have this picture here. So let's say we start when Earth's orbital position is at day 1, with both the sun and some distant star directly in line with the zenith for the observer on Earth. Now, because Earth moves around the sun roughly about 1 degree per day, after one complete rotation of Earth relative to the stars, we do not see the sun in that same position. So, to complete a solar day, Earth actually must rotate an additional amount equal to 1/365th of a full turn. Now, the time required for this additional rotation is about 4 minutes, such that a solar day is about 4 minutes longer than a sidereal day. And so that's going to get us to a different conversation. Let's start by talking about apparent solar time. And we can define apparent solar time as a time reckoned by the actual position of the sun in the sky, or during the night, because if we can't see it because it's below the horizon. This is the kind of time indicated by sundials. And it probably represents the earliest measure of time used by ancient civilization. They put the sundial and they would use it to kind of keep track of the position of the sun to really say, okay, the sun is at 1 o'clock, 2 o'clock, etc. Now today we adopt the middle of the night as a starting point of the day and measure in time hours elapsed since midnight. Before, they would kind of use noon as kind of like the starting point of the day, or you might see civilizations that use when the sun comes up, but we have adopted midnight as the start of our new day. And though apparent solar time seems relatively simple on the surface, it's just simply due to the position of the sun, it's actually not very convenient to use. The exact length of an apparent solar day varies slightly during the year. As we think about it, we of course have more hours of sunlight as we approach the summer solstice, and we of course are decreasing that as we reach the winter solstice. The eastward progress of the sun in its annual journey around the sky is also not uniform because the speed of the Earth actually varies slightly in its elliptical orbit. Another complication is that Earth's axis rotation is actually not perpendicular to the plane of its revolution. Thus, apparent solar time does not actually advance at a uniform rate, so going from day to day. Now, after the invention of mechanical clocks that do run at a uniform rate, it actually became necessary to abandon the apparent solar day as a fundamental unit of time. And so that got us into this concept of AM and PM. Now, during the first half of the day, the sun has not yet reached the local meridian, which is, of course, the great circle in the sky that passes through its zenith. We designate those hours as antemeridium or AM before the sun reaches the local meridian. Now, we customarily start numbering the hours afternoon over again and designate them as post-meridium or PM after the sun reaches the local meridian. Now, of course, there are designations for things like military time, which runs on a 24-hour clock, but for most of the world, AM and PM is a pretty standard function. And so another thing we can look at, though we already talked about apparent solar time, we can talk about mean solar time. See, one of our options that we have when we're trying to figure out actual time is to use mean solar time, which is based on the average value of the solar day over the course of a year, as each day contains exactly 24 hours. Now, although mean solar time has the advantage of progressing at a uniform rate, because that was one of the issues with apparent solar time, it is still inconvenient for practical use because it is determined by the position of the sun. For example, noon occurs when the sun is highest in the sky on the meridian, but is not necessarily at the zenith. But because we live on a round Earth, the exact time of noon is as different as when you change your longitude by moving east or west. If mean solar time were strictly observed, people traveling east or west would have to constantly reset their watches as the longitude changed just to read the local mean time correctly. Because, if you went and started moving, to the east, you're constantly going to have to speed your clock up. If you're going west, you're constantly going to spin it backward. So what can we do to solve this? Well, that's when we get into this conversation about standard time. Today, most of the world uses a system of 24 standardized global time zones. Within each time zone, all places keep the same standard time, with the line of longitude running through roughly the middle of each zone. Now, travelers reset their watches only when the time changes amounted to a full hour. So Pacific Standard Time, for example, is 3 hours earlier than Eastern Standard Time. Now, you might have heard, of course, about Daylight Savings Time. Now, Daylight Savings Time is simply just our local standard time plus 1 hour. This has been adopted for spring and summer use in most states in the U.S., as well as many countries, to really effectively prolong the sunlight into evening hours. It does not, of course, actually save any daylight at all, because the amount of sunlight is not determined with what we do with our clocks. Now, of course, you might have noticed some problems here if you think about this time that we are standardizing with. The fact that time is always advancing as you move toward the east gives us a problem that we have to solve. If you pass into a new time zone, on the average you're moving about 15 degrees of longitude with each travel, and each time you're going to set your watch ahead about an hour, which is easy enough in concept. However, by the time you've completed your trip, you have set your watch ahead a full 24 hours and thus gained a day over those who stayed at home. So how did we solve this? Well, we had to come up with the international dateline to really address this issue. So the solution, of course, as I mentioned, is the international dateline, which is set to run approximately along the 180-degree meridian longitude through the middle of the Pacific Ocean. By convention, at the dateline, the day of the calendar is changed by 1 day. So crossing the dateline from west to east, thus advancing your time, you compensate by decreasing the date. Crossing from east to west, you increase the date by 1 day. And one thing you'll notice too about the dateline, you'll notice there doesn't seem to be any actual countries on the international dateline. In fact, it's not even necessarily a straight line because it zigzags around to kind of try avoiding, like, for example, countries in two, or even just cities or anything like that, so that way we don't have to worry about any kind of weird wonkiness. But it's approximately around that 180-degree meridian.